remember something from pre-cal. Write the equation of a circle centered at 0, 0 with a radius of 5. Good, H and K, that weird formula. If you don't know it, and before you take the next ACT, you need to know that formula. You know what I'm talking about? This formula for the equation of a circle. It's on every ACT at least once, sometimes twice. That one. So if you don't know that before next ACT, you should work on it. Ours is a little easier because it's centered at 0, 0, so the H and K are both 0. So x squared plus y squared equals 25. Get y by itself and find dy/dx. This turns out to be some work because we're going to solve for y. It's a little complicated. Today we're going to learn shortcuts at doing functions that look like this or equations that look like this that are a little bit more complicated.
So you did the equation at the very top. So you just plug in 5 for H and K.
I plugged in 0 for H and K because the center was at 0, 0. And I plugged in 5 for R for the radius. And again, write that equation down, star it, for not necessarily for calculus. Occasionally it comes up in calculus, it is a rarity. But it comes up on the ACT. Everyone I've ever seen has a circle equation on it. More for ACT than for calculus. Get y by itself. I'm going to do that fast. I think you could all do it. Factor x over and then square root. Don't forget, if you square root, you have to do a plus or minus. When I do the derivative, what rule does it involve? Power rule and chain rule. It's got it inside, so I'll have to remember to do the chain rule. So dy dx or y prime, whatever you prefer to call it, is 1/2, leave the inside alone to the negative 1/2. Times the derivative of the inside. You could leave it like that, but just a little simplification. The 2 and the 1/2 will cancel. So we can just get plus or minus negative x over the square root. And you could even technically leave off the negative x if you wanted to, because the plus or minus is going to get it either way. Okay, so that's dy dx. And would you all agree that was a pretty yucky derivative? Not the worst we've seen, but pretty yucky. Use that derivative to find the tangent line at 4, 3. So this is a review from yesterday. How do you find a tangent line? What are the 3 things you need? X, y, and slope. I already have x and y, 4 and 3. That's nice. I need the slope, and how am I going to get the slope? Plug in 4 in for x into this equation over here. So we get negative 4 on the top. Maybe we'll talk about that. And then 25 minus 16. What's 25 minus 16? 9. So I do get some sign of 4 over 3. Does everyone agree? Question is, what's the sign? Well, I'm going to go look at the picture really quick. What is the sign right there? Does everyone agree it's negative? What that particular tangent line would be, it would be a negative value. I did need to look at the picture to find that, though. You can kind of tell why there would be a plus or minus. There is another value at 4. Does everyone agree? 4 didn't tell us which part of the circle we were on. The 3 told us which part of the circle we were on. So that'll be some things we can look at today. Today we're going to learn what's called implicit differentiation. There are 2 types of equations. There are implicitly defined equations and explicitly defined equations. Explicitly defined equations are the ones you're used to. They're y equals. Things you can type in your calculator. They're nice. Implicitly defined are things like x squared plus y squared equals 25. And in pre-cal, almost everything could be written explicitly. But have you seen some equations you would not want to solve for y? Like y squareds and y cubes and weird yucky things. So we would like to be able to take derivatives without always solving for y, just because it can be tedious. So this is a shortcut to doing what we did on the bell curve. Before we get too far into that, we need to go back to kind of the basics of a derivative and look at what we can do with things like the derivative of x to the 4th. So this one asks us to find the derivative with respect to x of x to the 4th. Well, I know that derivative is, you tell me what. But then I have to kind of ask myself what in the world this means. It asks me the derivative with respect to x, but then it says y to the 4th. Well, y could be anything, right? Could it be 3x? Could it be 5x squared? Could be anything, right? So when I do the derivative of y to the 4th with respect to x, what will I have to do? The derivative of the y, right? The chain, I need to do the chain rule, right? I don't know what y is, so I have to know that there's a derivative of it in here. And so what I'm going to do is I'm going to multiply by dy dx. And so again, let me explain to you what that means. Y could be 3x, right? I don't know what y is. If it were 3x, wouldn't you have 3x to the 4th power? In which case, when you did that derivative, you'd have to do a chain. So that's where this is coming in. Y is some function of x that I don't know what it is. So anytime I take a derivative with a y in it with respect to x, I'm going to have to do a dy dx. So that's newness. So let's look at some more examples. I have the derivative with respect to x of x plus 5. Well, what's the derivative of x with respect to x? 1. Always has been. That doesn't change. But then what's the derivative of 5y? 5, and then whatever the derivative of y is. I don't know what y is, so it has some derivative. So 2 ways we can write it. Both of those are correct notations for what we'll be working with. So either way, chain rule, chain rule, chain rule. If I take a derivative of something other than x, I have to do times y prime, or times dy dx. Any questions so far? What do I need to do on the next one? Product rule. Very good. That's the most common mistake with implicit differentiations, forgetting to do a product rule. Left, d right. What's the derivative of y? Derivative of y, right? You can write either one. You can write y prime or dy dx. Both are wonderful. I don't care which one you write. If you have sloppy handwriting, I would suggest dy dx. If you have pretty handwriting, do either one. Now, the reason I would suggest dy dx if you have sloppy handwriting is those little crowns get lost sometimes if you aren't careful. Plus right, d left. That's it. And so this is kind of leading us up to being able to do the bell ringer easy. remember I solved for y, which wasn't impossible, and I used a chain rule. Not horrible, but I think there's an easier way. So what I'm going to do is I'm going to leave this in implicit form. I'm not going to rewrite it as y equals. I'm not going to get y by itself. And I'm just going to take the derivative of the whole thing with respect to x. So every piece in there, I'm going to take the derivative of it. So what's the derivative of 2x? Or 2x. What's the derivative of y squared? 2y dy dx, because we took the derivative of 2y prime. Yes, if you want to use the other notation, 2y y prime. And what's the derivative of 25? 2. Now I can get dy dx by itself. Divide by 2y on both sides, I get negative x over y. Does everyone agree? Just getting it. Divide by 2y. I would argue I found the exact same thing I found in the bell here. Remember I made you find the slope at 4, 3? Well, what would this be at the x value 4 and the y value 3? You just put 4 and 3 in, right? But you get negative 4/3. In fact, I'll even have the correct sign on it, because you took into account the y value also. I think it worked. Would you agree this was easy? I got dy dx, which is y prime by itself. So I divided that into 2y. So I found the derivative, what's called implicitly. If you really wanted to see that they were equal, you could go replace y with the y value, which would be the plus or minus the square root of 25 minus x squared. You got the exact same thing, just a little nicer. So, summary of how to do implicit differentiation. These are kind of your those of you who are step-by-step people. The second way was much easier. Tells us more about the derivative because it takes into account y as well. So, step 1, it's really, they called it step 0. Imagine that y is some function of x. So we're going to keep in mind that y is some function of x, but we don't know what it is. Take the derivative of both sides of the relation using the chain rule every time you see a y. So every time you do a derivative with y, put dy dx or y prime, whichever one you prefer. Collect all the y prime terms on one side of the equation and solve for y prime. And I put a little hint there. You'll need to factor out y prime most of the time. And if the question asks about a specific point, plug that in. So if it were a tangent line at the point 4, 3, plug in 4, 3. So remember that y is some function of x. Take the derivative every time you do a derivative of y, put a dy dx or a y prime. Collect all y prime terms on one side of the equation and solve for y prime. Now, as you're writing, I want to have food for thought. The one on the bell ringer was not terrible solving for y. It was doable. Look at the one I have up here. Would you want to solve that for y? And then do a derivative? Probably not. It's actually still doable. You could get the y cubed terms on one side and factor out a y cubed, then divide, then take the square root or cube root. It is doable. Now, there will be some that aren't doable. This one is, but I don't want to. And so that's where implicit differentiation comes into play. pick out any product rules before you start. Are there any product rules in this example? Where? X squared times y cubed, right? Just mental note those in your brain when you're new at this before you start. Don't forget a product rule. So we have a product rule right there. So when I do the derivative of the whole thing, right? On that first piece, if you are finished writing, go ahead and try it. We have left times the derivative of the right. What is the derivative of y cubed? 3y squared times y prime. Y'all like y prime better? I'll do one with y prime. And this one I'll do with y dx. They incorporate. Okay, any questions? That's lefty right plus right left. What happens to the 6? It's 0, right? The derivative of a constant is 0. What about the 5y cubed? Why do you need a y prime in? The derivative of y. Anytime you take the derivative of y. Any questions so far? Now, remember my goal was to find the derivative, find y prime. So I'm going to take all the y prime terms, and you'll notice I actually have 2 of them. All the things with the y prime in them. And I'm going to put them on the same side of the equation. It doesn't matter which side you go to, but on the same side of the equation. I'm going to go to the left with the y primes. So I have 3x squared y prime minus 15y squared y prime. And then I'm going to subtract the 2xy to the other side. Okay. Any questions so far? I'm going to factor out the y. Oh, question.
Where did it come from? Did you?
This one? Yeah, I just moved it. Okay. Yeah. And you could leave it there if you wanted to. Yeah, I just rearranged that piece. I'm going to factor out a y prime. In the future, you will start factoring this out as soon as you subtract over. When you get all the y primes together, you'll kind of factor at the same time. But for now, we'll do it one step at a time. And then divide by the 3x squared y squared minus 15y squared. Get y prime by itself. That was our whole goal to begin with. So it looks a little yucky, but it's a derivative. If I needed a tangent line or something, all I have to do is plug in x and y, and I'd be good to go. So, any questions? I think I'm going to skip the first one. It's one is one that trips people up a lot because of the negative in front of the 3x squared y. So see if you can do this. Okay. So the first piece, what's the derivative of x cubed? Any questions so far? The second part is where it gets a little tricky with the negative in front, and you have a couple of options. You can either factor it out and put parentheses, or you can call the left-hand side of this function negative 3x squared. That's probably what I would do, but just make sure that you get the negative in with both pieces. Does everyone know what I mean by that? Somehow the negative has to go with both the left and the right when you do those derivatives. If you kind of leave it as your left-hand piece, it works great. If you factor it out, it works great. But then a lot of people do forget to put the parentheses. So I'm going to do left, d right, plus right, d left. And when I do d left, I'm going to call that negative 6x. You see what I mean by the negative having to end up in both pieces? A lot of people mess that one up, so I wanted to do an example of that. That's how I like to do it, just leave the negative as part of the left and work with it, but somehow get that negative to both pieces. Actually, it has two product rules, doesn't it? Left, d right, plus right, d left. And then the derivative of 12 is 0. Find every term that has a dy dx with it. So this one does, and this one does. And get those on the same side of the equation. It doesn't matter what side you put them on, but they need to be on the same side. Which side did y'all go to?
But where does 12?
So what's the derivative of a constant? Good question. So you'll put the dy dx on the left. So 4xy, I did do a little bit of combining there. 2 times 2 is 4. Minus 3x squared.
I can cancel out. There's the x squared.
I am going to move it to the right. I haven't done anything with it yet. So far I just took the 2 pieces with the dy dx and put those there.
I think the rollback has a job. That's it.
Not that I've seen. Look back on that back shelf.
Okay.
No one's brought me.
Alright, thank you.
So all I did was bring those down. Now what I am going to do with everything else is subtract it over to the right. So the negative 3x squared, this is a negative 6xy. So what will it be when I move it over? And then minus 2y squared. Again, a lot of you will do this next step combined in with that first step when you start doing these more often. But you will factor out the dy dx. Do you see how you could combine those 2 steps into one? You know you're about to do it. You can just take the dy dx out. Good. And then divide by 4xy minus 3x. Any questions so far? Okay, I'm going to stop there just because I feel like your brain could handle me stopping there. We are not finished with implicit, so a couple of things I want to show you that we will do tomorrow. We will do tangent lines, although I figure you could do that even with me stopping right now. You just plug in a point to get this slope. But we will do some tangent lines tomorrow. There are some tangent lines on there, so if you don't feel comfortable, you can wait until tomorrow. It's up to you. We will find horizontal tangents and vertical tangents tomorrow, so if there's one of those, I probably skip it. And then we will find the second derivative implicitly tomorrow. So those are the things we will do tomorrow. We will save those for tomorrow. And the homework, you won't get any new homework tomorrow. So, again, if there's something you don't know how to do, don't stress about it. There's only 11 problems. You'll have plenty of time to do them tomorrow. I would go ahead and do 1 or 2 implicit derivatives just so you kind of get your brain working with that so that tomorrow when we ask steps to it, you have a couple. But then you might want to